So now, before I continue with our next slides in here, let me go back to the following slide in here and talk about more things with regards to the or the union, okay, and the word "and" here, okay. So I will introduce another symbol that will correspond to the word "and." Okay, so I mentioned that for the word "or," the symbol corresponding to that is this symbol, and it is called the union. Okay, it's called the union. And when we say union, we mean we combine the solution set uh, on this side with the solution set on this side. Okay, so graphically, let's look at that. Graphically, if this is your real line, okay, this is your negative 3 here, and this is your positive 3 here, okay. This guy here, x less than or equal to negative 3, it means that we are taking all the x's on this blue ray, okay. So x less than negative 3, okay. And then for this guy here, x greater than or equal to positive 3, it means we are taking the we are taking all x's starting from positive 3 going to the right. Okay? So when we say or union, we combine all this set. Okay? This set here and then this set here, we combine them into a single solution set. Okay, so that's why you both put this into a single real line. Okay, so this is the word or, okay, or the symbol union. Now, what about the word and? Okay, so for the word and, the symbol we are going to use here, or the symbol corresponding to the word and, is this guy here, and we call this the intersection. Okay, we call this the intersection. So graphically, we have this x greater than or equal to 3 and x greater than or equal to negative 3. So for example, this is your real line, this is your negative 3, and this is your positive 3. We have here x greater than or equal to 3. Okay, that one is this part. So you have this 3 here. Okay, and then you want all x's greater than 3. So you are going to the right, or this ray points to the right. And then for this guy, your x is greater than or equal to negative 3. You also construct the ray that points to the right. Okay, that points to the right. And the word "and" here tells us that these two guys here must be both satisfied. So it must be x greater than 3 and x greater than or equal to 3 and x greater than or equal to negative 3. And graphically, this is that part. Okay? Because like how I um, illustrated this before, if I get an x in here, I don't get an x coming from this set. Okay? But if I get my x in here, I also get this x here. So this x here is both on this ray and on this ray. So basically, we just intersect this ray with this ray, and the resulting is just this x greater than 3. Okay? X greater than 3. That's why here on this side, okay, on this side, you only get your x greater than 3 as, or greater than or equal to 3 as a solution of this condition. X minus 3 greater than or equal to 0 and x plus 3 greater than or equal to 0. Okay? If you do this, okay, if you do this, what you will get is the following. So let us try to sketch. So same, you have here your real line, and then you have your negative 3 here, positive 3 here. You want your x to be less than or equal to 3, so your graph will be something like this. And then you also have x less than or equal to negative 3, so your graph will be something like this. Okay? And since you have the word "and" in here, you want the intersection of the two rays. And the intersection will be this guy here. Okay? Which means coming from this case, what you only get is x less than or equal to negative 3. Okay? Now, because of the word "or," okay, the word "or" here, this is what you will get. Okay? So x greater than or equal to 3 or x less than or equal to 3. And as you notice in here, this guy here came from this. Okay? So this side here came from this, or came from the first case here, while this guy here came from this, the second case in here. Okay? So again, if you have the word "or," you use union, meaning you combine, okay? You combine all together all the solution sets that you obtain. While if you have "and" or the intersection, okay, you just get what is common to them. So here, x greater than or equal to 3 and x greater than or equal to negative 3, what's common to them is that x greater than or equal to 3. Okay? So, or, union, and intersection. Okay? So we will use this. We will use this intersection now. Let us go to our next slide in here. So we now define operations on functions. And the operations are very much similar to the ones we already know. Okay? Recall that we talked about operations on expressions, okay? Or operations on numbers, addition, subtraction, multiplication, division. We also use them, okay, to operate on functions, okay? So, for example, let f and g be functions, okay? We want the sum of f and g, okay? So it's f plus or minus g of x, okay? This is f of x plus or minus g of x, okay? So the function f plus g, okay, f plus g, or the function f minus g, okay, with variable x, it's just the function that is obtained when you add or subtract the function f of x and g of x. Okay? But our main interest here is the domain of the function f plus g. The function f plus g, it will have the domain intersection. Okay? Intersection of the domain of f and the domain of g. Okay? Meaning, this sum here is only defined when both f of x and g of x is defined or are defined. Okay? So, common to both the function f and function g. Okay, so that's sum. And take note, I say sum and you see subtraction. Okay, it's still sum. Okay, if you recall, we already defined the subtraction by means of addition. You have your f minus g. Okay, this is just defined to be f plus the negative of g. So it's still sum, even if you see that subtraction. Okay, so that's for the sum. Product. So you have two functions f and g. You define now the product fg. Okay, so fg of x in here, this is the function, okay, obtained when you multiply, okay, the function f of x by the function g of x. Okay, so the product fg, it's another function. It's obtained by multiplying f of x and g of x. And again, if we want to find the domain of the product fg, okay, we just get the intersection of the domain of f and the domain of g. So those that are defined, so you get all x's that are defined on both f and g. Okay? Questions so far? Next function, quotient. Okay? The quotient f over g. Okay? F over g of x. This is obtained by dividing f of x over g of x. Okay? So the quotient f over g of x is the function obtained by dividing f of x over g of x. Now, look at the domain. Look at the domain of this quotient. Domain of f over g, this is, okay, this is the set obtained by getting the intersection of the domain of f and the domain of g. Okay, and then you take out all the excess that will make the denominator 0. Look at that. Your g of x is now denominator. So there's a possibility that this g of x will be 0 at some numbers. So aside from getting the domain of your the domain of f and the domain of g, aside from getting the intersection, you also remove those x's that will make g of x equal to 0. Okay, so take note of that. This will be clearer when we consider examples later. And lastly, we will define the following operations. This operation is called composition. Okay, so you see here f circle g. This is circle. F circle g. This is read as f of g. Okay, f of g. So f of g of x, well, this is how we get it. You evaluate the function f by the function g of x. Okay, so f of g of x. The domain will be a bit complicated, but this is how we define it. The domain of f circle g, it is equal to all x's that first you get it from the domain of g, because in here you evaluate the x at g first. Okay, so you get your x from the domain of g, and then you will get some number because, well, x is from the domain of g. Your g of x will be some number. Okay, now you have to make sure that the g of x, the number you got, where after you evaluate your x in g, so the g of x, you have to make sure that that g of x is inside the domain of f. Okay? So again, look at this. You get your x, you get your x, you evaluate your x at g. So you will have your g of x. Okay? Of course, g of x will be a number. You have to make sure that f of that number, okay, f of that number is also defined. Okay? So from your original x, you will get your g of x, and you use that g of x to evaluate in f. Okay? So again, like I said earlier, these two guys, particularly the domain of the quotient, and here, the composition and of course the domain of the composition will be clearer when we discuss the examples I have provided. First, look at this. Let f of x be the function x minus 1 over x plus 2, g of x equals x plus 2 over x plus 5, and then h of x equals x minus 2 over x plus 5. Okay? So f of x equals x minus 1 over x plus 2, g of x equals x plus 2 over x plus 5, and h of x equals x minus 2 over x plus 5. So we want to find the domain of f, the domain of g, the domain of h. And then we also want to find f of negative 4, g of negative 4, and f circle g of negative 4. Okay? So let's do this. First, we have the domain of the set, the domain of f. Okay? So this is your f. Notice you have a denominator x plus 2. Okay? You have a denominator x plus 2. You don't want your denominator to be 0. But x plus 2 will be 0 when x equals negative 2. So meaning, you don't want your x to be negative 2. And then for all other numbers, okay, for all other numbers, the function f of x is defined. Okay, meaning our only restriction is that x cannot be negative 2. So the domain of f, it's the set of real number except that negative 2. So you remove that negative 2. Okay? Question so far? That's easy because this is just a rational expression and we don't want our denominators to be 0. So this is a rational expression, this is a rational expression, this is a rational expression. They define the functions. We just don't want the denominators to be 0. So we easily get domain of the function g. This is our function g. The denominator is x plus 5. Okay? We don't want our denominator to be 0, so we take away x equals negative 5. Because when x equals negative 5, the denominator here will be 0. So we remove that x equals negative 5. Therefore, the domain of g, it's the set of real number except negative 5. Okay? And the next, domain of h. This is your function h. And notice the denominator is also x plus 5. So we have the same domain for h, the same as the domain of g. So the domain of h, it's the set of real numbers except negative 5. Okay? Questions so far? Next, we try to find f of negative 4. So all we need to do is to replace the x's here, okay, with negative 4. So you have an x here, you have an x here, you both replace it by negative 4, so that's f of negative 4, that's equal to negative 4 minus 1 all over negative 4 plus 2. In the numerator, you will have negative 5. In the denominator, you will have negative 2. So negative 5 over negative 2, that's just 5 over 2 here. Okay? And then for g of negative 4, again, we just evaluate here. Look at this. At negative 4, you have x plus 2 over x plus 5. So when x equals negative 4, you will have negative 4 plus 2, okay, over negative 4 plus 5. In the numerator, you just have negative 2. In the denominator, you have positive 1. So g of negative 4, that's negative 2. Okay? So easy calculation, at least for f of negative 4 and g of negative 4. Now, let's look at f circle g of negative 4. So this guy here, by definition, it's this one. Okay? F circle g of negative 4, this is equal to f of g of negative 4. Okay? So written this way, you see immediately that you have to evaluate the negative 4 to g. Okay? So you evaluate g at negative 4. But we already have your g of negative 4 here. G of negative 4, according to this computation, g of negative 4, it's negative 2. So we replace g of negative 4 by negative 2. So now you have f of negative 4. Okay? F of negative, sorry. We now have f of negative 2. Okay? But notice, look at this. The domain of f is the set of real number except negative 4. Except negative 2. But now we are evaluating f at negative 2. And in fact, if you replace your negative 2 here, okay, with the x's here, you will have a 0 denominator. Okay? Which means this is actually undefined. Okay? Meaning f circle g of negative 4 is undefined. Okay? So again, notice we started with f of negative 4 and we got a value, 5/2. We calculated g of negative 4 and we got a value, negative 2. Now we calculate f circle g of negative 4, which is equal to f of g of negative 4. But g of negative 4, it's negative 2. So we have f of negative 2, but f is not defined at negative 2. So all in all, f circle g of negative 4 does not exist. Okay? Question. So if you have the course notes, you can write these answers here. So again, for the domain of f, domain of g, and domain of h, you just study the function itself. Here you have a rational expression for f, also for g and for h. You don't want the denominator to be 0. So you solve for those x's that will make the denominator 0, and then you remove it from the set of real numbers. So for the function f, denominator is x plus 2. If x plus 2 equals 0, then x equals negative 2. Then you remove that negative 2. For g of x and h of x, denominators are the same, which is x plus 5. So we solve for x plus 5 equals 0 and get x equals negative 5. We remove that x equals negative 5 from the domain or from the set of real numbers, and you will get the domains of g and h. For these two guys, f of negative 4 and g of negative 4, it's just evaluation. So you replace, okay, you replace the x with negative 4 here. In here, you replace the x in g with the negative 4 here. But be careful when computing for f of g of negative 4. Because f of g of negative 4, this is defined to be f of g of negative 4. So you replace negative 4, okay? You replace the x in g with the negative 4 and only to the function g. So after getting that, you have your negative 2. So now you have f of negative 2. Okay? And the same, you replace it. You replace now the x of the function f with negative 2. It just so happened that when you do that, the denominator will be 0. That's why we have undefined. Okay?
I have a question.
Sure.
Uh, g minus 4 is will be always minus 2 because
Yeah, because you calculated it here. You see? You just replace your x with negative 4. It's just calculation.
Mhm. Like you take minus 2 and just function minus 2, that's it. Like,
You mean for this part?
yes, how
It just so happened because you have here g of negative 4, but you already calculated g of negative 4. It's equal to
so
negative 2,
it mean
right?
g minus 4 always minus 2, yeah?
For this guy, yes. For this guy. For this
Mhm.
guy, because this is your function g.
So they have kind of connection between the two.
Yes. Yes.
Okay, thank you.
You're
Why
welcome.
we don't do exercise for age?
We did
Okay.
just the domain.
Ah, that's it.
Yeah, that's the
Ah,
domain.
okay, thank you.
But we will see. Possibly we'll see that again later. Okay?
Mhm. Thank you.
You're welcome. Other questions? Next, you have f of x, same function f of x as in before, x minus 1 over x plus 2. The function g of x, you have x plus 2 over x plus 5. Now you want f plus g of x. So you want the sum of f and g. Okay? And you also need to find the domain. So by definition, f plus g of x, this is simply f of x plus g of x. So you just copy the function f and the function g, and then you add them. So now you are just adding rational expression. And we have done a lot of this kind before. So you combine, okay? So the denominator, it's just the product, x plus 2, x plus 5. The numerator, you cross multiply. So x minus 1 times x plus 5 plus x plus 2 times x plus 2. And then do the simplification. So in here, we multiplied this guy here and then this guy here to obtain this numerator here. And finally, after simplifying the numerator, we will have 2x squared plus 8x minus 1. The denominator, it's just x plus 2x plus 5. And you don't have to multiply this x plus 2 times x plus 5. You just write it in factored form. Okay? Now, the domain. The domain. The domain of f, earlier, we already got it. Okay? We already got domain of f to be the set of real numbers except 2. Okay? So this is what we got from the previous domain of f. It's the set of real numbers except negative 2. And then you have the domain of G. This is the set of real numbers except negative 5. Correct? So the domain of f plus G, we get the intersection of f, of the domain of f and the domain of G. So in here, we have, let's draw that. So for this guy, you have your negative 2 here. You get all the real numbers except for negative 2. Correct? And then for this guy, this is your negative 5 here. You get all the real numbers except for negative 5. So, what's the intersection? The intersection is the set containing all the numbers that are common to this. This guy here has negative 5, but this guy here does not have negative 5. So it's not common to both of these. This guy here has negative 2, but this guy here does not have the negative 2. So again, negative 2 is not common. All other numbers are common to both domain of f and domain of G. Which means, if we get the intersection, okay, it will be the set of real numbers except negative 2 and negative 5. Because negative 2 and negative 5, each of them, okay, is not common to both. Okay? Negative 2, it's not allowed, or it's not in the domain of f. Negative 5, it's not in the domain of G. Okay? And that will be the domain of f plus G. So intersection. What is common between the two domains? Okay? Question. Next, let's look at the product fg of x. Let's look at the product fg of x, and then we find the domain. So, by definition, fg of x, it's just f of x times g of x. We replace f, okay? We use the function here, f, and we use the function g, and then we just multiply them. But notice, if you multiplied them, x plus 2 here will cancel. Okay? The simplified version of f of x times g of x will be x minus 1 over x plus 5. Correct? So look at the simplified version. X minus 1 over x plus 5. Now, what is the domain of f times g? Just like before, it should be the intersection of the domain of f and the domain of g. So it's the same as the sum. You still have the domain of fg. It's the set of real numbers except negative 2 and negative 5. Okay? Now, you might ask, Sir, why in the simplification of the product fg, okay, we only have denominator x plus 5? Okay? This rational expression here means that the domain is just the set of real numbers except negative 5. But why do we include negative 2 to be removed from the set of real numbers? Again, it's because coming from the definition, you need to get the intersection of the domain of f and the domain of g. That's why you also remove negative 2. Furthermore, if you have this expression, take note that you can only cancel x plus 2 with this x plus 2 if it is not equal to 0. Okay? Remember this property. AB over AC, this is equal to B over C, but your A must not be equal to 0. So remember this. This is your cancellation law. And take note, x plus 2 will never be 0. Why? Because you removed it from the domain of f. Okay? X plus 2 will never be 0, and therefore you can cancel them. Okay? So, do not be deceived by the simplified version of your functions. For example, this, your function fg. The simplified version, it only has the denominator x plus 5. But take note, the domain of the function fg is derived using the domain of f and the domain of g. Okay? Question. Question. Let's now go to our next example. Here, you have your function f of x, x minus 1 over x plus 2. And now, let us use h of x minus 2 over x plus 5. We want to calculate f over h of x and its domain. So by definition, f over h of x, this is just f of x divided by h of x. And then we do this. So we replace the function f of x by x minus 1 over x plus 2. And then you have this long bar here. So all over, you replace your h of x by x minus 2 over x plus 5. Okay? But this is just complex rational expression. So we can rewrite this in the following manner. So this guy here, we change this to multiplication, but we need to get the reciprocal of this denominator. So you will just have x minus 1 over x plus 2 coming from the big numerator. And then here you have x plus 5 over x minus 2, the reciprocal of your big denominator. Okay? And then we'll just rewrite it this way. So x minus 1 times x plus 5 over x plus 2 times x minus 2. So this is the quotient f over h. Okay? So again, let me write here domain of f, it's the set of real numbers except -2. Domain of h, it's the set of real numbers except -5. Okay? But now, your h of x is a denominator. Okay? Your h of x, it's a denominator. So we need the x that will make h of x equal to 0. Okay? You have h of x equals x minus 2 over x plus 5. This is equal to 0 if x minus 2 equals 0, which implies that x is equal to 2. Okay? Meaning, h of x will be equal to 0 when x equals 2. Following? So let me copy this part here. Now, our goal, find the domain of this function. Okay? Find the domain of this function. We have the following. By definition, okay? By definition, the domain of f over g, it's the domain of f intersection the domain of h. Okay? So let me enclose this with that parenthesis. So domain of f intersection domain of h, take away, take note of that, take away all the excess that will make h of x equals 0. So the domain of f intersection domain of h, so these two guys here, it's the set of real numbers, remove -2 and -5. Okay? So domain of f intersection domain of h, it's the set of real numbers, you remove -2 and -5. For this guy here, we also remove all the excess that will make h of x equals 0, but h of x equals 0 when x equals 2. Which means the domain of f over h, it's the set of real numbers, you remove -2, -5, and +2. That's why you have that +2 there. Okay? Question. Now, look at the simplified version. Your f over h of x, it's x minus 1 times x plus 5 over x minus 2 times x minus, over x plus 2 times x minus 2. Of course, in this simplified version, you see x cannot be -2 and x cannot be +2. So you will see immediately that you need to remove -2 and +2. But if you only look at this, you might not be able to see that your x cannot be -5 also. Because originally, x plus 5 is a denominator. It's a denominator of h. Okay? question? So I'm giving another 10 seconds. Maybe you have questions in mind.
For the domain of f equals r, it's remove 2, -2?
Yes, that is
And
correct.
that's because, uh,
You have this. Your x
okay,
plus 2 is a denominator, and you don't want that to be 0.
so we make x plus 2 equals 0, and then bring it to the other side, so x equals -2.
Mhm.
And that gives us domain of f.
The domain of f, well, um, as a rule, if you have only rational expression, okay, if you only have a rational expression, you always start with the set of real numbers. That's why you have this. And then you choose the numbers to be removed. You choose it by solving for the denominator equals 0. So x plus 2 equals 0. And you solve that, x plus 2 equals 0, x equals -2. So you remove it. Similar to this, your h of x. It's a rational expression. Start with the set of real numbers. That's why you have r here. And then you choose all the numbers that will make the denominator 0, and you remove it. So x plus 5 equals 0, or x equals -5. So you remove -5.
So how come we did the for h of x equals the last thing we did? How come we
But
did the x minus 2 equals 0?
because your h of x is a denominator, okay? So there's a possibility that the denominator will be 0, this guy here. So you solve for h of x equals 0. You don't want your h of x to be 0. Because, again, your h of x now, the whole h of x is a denominator. So you solve that.
Okay.
Yeah, you solve that. But this will be true if x minus 2 is equal to 0. Okay? It's just the numerator here equals 0. That's why you have your x minus 2 equals 0. That's why
Okay.
we have solved x equals 2.
Thank you.
You're welcome. And since, again, h of x is a denominator, you remove that. You remove that. Because if you included 2, it will mean your denominator will be 0. And you don't want that. So those are the 3 numbers that you need to remove. The -2, it came from the function f, the original function f. So you have to remove that. The -5, it came from the function h. You have to remove that because the denominator of the function h is x plus 5. The +2 here, it also came from the function h, but this time it will make the function h 0. But h is now a denominator. So you don't want that also. Okay? Other questions? Okay. Let us now consider the composition. So we bring back the function g. We now solve for f circle g of x and its domain. Okay? So with this exercise here, you will see how we actually do your f circle g. So by definition, f circle g, this is f of g of x. So meaning, this g of x here, this g of x here, it will replace both x's here. Okay? So, we have the following expression. So, your x here and your x here, it is now replaced by g of x. Okay? And then, we now replace your g of x with the function, the representation of that function, which is x plus 2 over x plus 5. So here, x plus 2 over x plus 5 for this part. And then you have the minus 1. Then the denominator, you have x plus 2 over x plus 5 plus 2. So you just replace it. And then you simplify this complex rational expression. So you can combine this guy here into a single rational expression. Similarly for this. So you will get this expression here. Please practice on this if you already forgot what to do. But you simplify. Okay. So you simplify the numerator here. It becomes what? X plus 2. And then here, you distribute the negative. You have minus x minus 5. So x minus x, that will cancel. 2 minus 5, that's your negative 3 here. Then, of course, your x plus 5 is in here. From division, we do multiplication now. Okay, so from division, you do multiplication now. So we get the reciprocal of this. That's why in the numerator here, it was the denominator here. For the denominator, you distribute these 2. So you will have 2x, 2 times 5, that's 10. So 2x plus x, that's your 3x here. And then your 2 plus your 10 here, that's your 12 here. Okay? And then, you see 3 is factorable in here. You can factor that out. And then, you will be able to cancel x plus 5 and x plus 5 in here. Now, this negative, I moved it here. I moved it at the very outside. But anyway, this 3 will cancel this 3 here. And finally, you will just get negative 1 over x plus 4. Okay? So just to emphasize the cancellation of the 3 here, I'll put it there. So look at this. From some complicated expression, it's reduced to negative 1 over x plus 4. Okay? So the question is, what is the domain of g of x, or f of g of x? If you only base your answer on this, you would only say that your x cannot be negative 4 because that's your denominator. Okay? You will only say that your x cannot be negative 4 because that is your denominator. Okay? But there's more to that. Because what is the domain of F circle G? By definition, you get all the x's coming from the domain of G. And then you should show that when you evaluate those x's, the g of x must be in the domain of F. Again, what is the domain of G here? The domain of G, this is the set of real numbers except negative 5. Correct? So, initially, this set here, this part here means you already removed negative 5. The next question is, are there more? are there more numbers that needs to be removed? Okay, so are there more numbers that need to be removed? You will be able to find that when you do this. Your g of x must be in the domain of f. But what's the domain of f? The domain of f, this is the set of real numbers except -2. Okay? So meaning, we don't want our g of x to be -2. Okay, let me do the computation here. So g of x element of the domain of f implies that your g of x must not be equal to -2 because you remove that -2 from the domain of f. Correct? So we solve this. We solve this. What will make, what x will make g -2? Once we found that out, we remove it. Okay? Okay? So let's see. Domain of G, it's the set of real numbers except -5. The domain of F, it's the set of real numbers except -2. Since your X will be coming from the domain of G, -5 is not included already. Okay? So look at the definition of the domain of F circle G. So this is the definition of the domain of F circle of G. So let X be in the domain of G, which means X cannot be -5 already. Okay? X cannot be -5 already. Then we need g of x not in the domain of f, but I already mentioned it's g of x not equal to -2. Then we solve this. We solve this. This means that this x plus 2 over x plus 5 cannot be -2. Okay? And this means if you multiply this to the other side, it means your x plus 2 cannot be -2 times x plus 5. And then you calculate. It means x plus 2 cannot be -2x minus 10. Further calculation, you will get x cannot be -4. So all you have to do, you put this to this side, your -2x, you put this to this side, your 2, you put it to the other side. And you will get 3x cannot be equal to -12, or x cannot be equal to -4. Which means the domain of F circle G is the set of real numbers except -5 and -4. So again, this -5 here came from this part. Your x must be in the domain of G, and -5 is not included. That's why you also not include that -5. While this 4, it's coming from this. Okay? So x cannot be -4, so you remove it. Okay? Question? Let's have another function here, or another set of functions. Your f of x equals 2x squared plus 1. Your g of x equals square root of 2x minus 1. And then you want to find f circle g and g circle f. Okay? You want to find f circle g and g circle f. So let's start with f circle g. That means you have f of g of x. Okay? So meaning, you replace the x here with your g of x. So 2 times g of x squared plus 1. And then, we now use the function g of x here. So we replace now g of x with square root of 2x minus 1. Then you square it. You will get 2 times 2x minus 1 plus 1. To simplify it, you just get 4x minus 1. Okay? What about g circle f? So this time, you want g circle f. This time, it is the f of x that is being evaluated in g. So look at the positioning. F circle g of x, f of g of x. G circle f of x, g of f of x. So the arrangement remains the same. Okay? F, G. F, G here. Here, G, F. So G, F here. Okay? So this time, you have the function G here. You have the function F here. You replace the x's in the function G with your f of x. So you have 2, or you have square root of 2 times f of x minus 1. And then, we now change your f of x with its representation. It's 2x squared plus 1. And then you just simplify. If you simplified, you will have square root of 4x squared plus 1. Okay? So what's the point? You have f circle g, you got 4x minus 1. And then you have g circle f, you got square root of 4x squared plus 1. They are not the same. Okay? So in general, f circle g is not the same as g circle f. So make sure that you have the proper arrangement when you are trying to compose one function with another. Okay? Now, how do you get the domain of f circle g here? You start with the domain of g of x, or the domain of g. Okay? Let's work on that. Okay? Let's look at the domain of f circle g. So again, this is the set of all x such that your x must be in the domain of g, okay? And that your g of x must be in the domain of f. But let's write what's the domain of f here. Domain of f This is a quadratic expression. This is a quadratic expression. So whatever number, whatever real number you use, you will have a value. The domain of F, it's the set of real numbers. For the domain of G, you have square root of 2x minus 1. So you need 2x minus 1 to be greater than or equal to 0. Okay? But this implies your 2x must be greater than or equal to 1, or this implies your x greater than or equal to 1/2. You don't want your radicand here. You don't want your 2x minus 1 to be less than 0. So you need this. 2x minus 1 must be greater than or equal to 0. Which means the domain of G, this is the interval 1/2 up to plus infinity. Okay? So, let's look at the domain of F circle G. So you start with the domain of G, meaning your x must be coming from this. Okay? Your your x must be coming from this. But now, you need the value of g of x to be in the domain of F. But look at this. We don't have any problem with that. Because the domain of F, it's the real number. If you get your x from this interval, g of x will just be a real number. And therefore, this is always true. This part here is always true. Which means, in here, this is just 1/2 up to plus infinity. That's the domain of F circle G. Okay? So again, domain of F circle G, x coming from the domain of G, such that your g of x in the domain of F. The domain of G, it's just this guy. So we start from this. We get all x's from here. But when you evaluate, of course, g of x will be a real number. And the domain of F, it's the set of real numbers. So we don't have any problem. So meaning, it's fine that we only get our x from this interval. Exactly the same as the domain of G. As for this guy here, so we want now domain of G circle F. But this means you have to get your x from the domain of F such that your f of x must be inside the domain of G. Okay? Question? Now, domain of F, again, it's the set of real numbers. So you start with that. You can get any real number because that's the domain of F. But you need you need your f of x. So you need your f of x to be in the domain of G. This means what's your f of x? It's 2x squared plus 1. Okay, that's your f of x. You need this to be greater than or equal to 1/2. Okay, but notice, this is always true. This is always true, whatever your x is. Because this is true for any real number x, for any x in the set of real numbers, since if x is from the set of real numbers, x squared will be greater than or equal to 0. Okay? Let me copy this guy here and adjust. Okay? Your x squared is greater than or equal to 0. And this implies that your 2x squared is greater than or equal to 0. And this implies that your 2x squared plus 1 will be greater than or equal to 1. And 1 is greater than 1/2. So this is always true. Okay? Let me write that always here. Correct? Which means the domain of of G circle F, this is just the set of real numbers. Okay? Question? Okay. So those are the 4 operations of on functions. We have the sum, it's addition and subtraction already. We have the product, we have the quotient, and we have the composition. Okay? So let's go back to that slide. So this guy here. Sum, you have the plus and minus. The domain of the sum, it's the domain, it's the intersection of the domains. You have the product, the domain of the product, it's the intersection of the domains. For the quotient, there's an additional condition. So domain of f over g, it's the intersection of domain of f and domain of g, but we take away all the x's that will make the denominator 0. For the composition f circle g, the domain of f circle g, it's the set of all x such that x is coming from the domain of the function g, such that the g of x is in the domain of f. Okay? So question for this. Okay, so our last topic for today will be graph of a function. So this is an recall the alternative definition of a relation. Let x and y be non-empty sets. A relation from x to y. This is any subset of the x cross y, the set x cross y. And the set x cross y is the set of ordered pairs x comma y, such that the first coordinate here will be coming from x. The second coordinate here will be coming from y. So I am using the same term, coordinates, because what we're going to do is to put it in the rectangular coordinate system. Okay? Now, the graph of a relation f, this is the set of all points x, y in the xy plane. That's your rectangular coordinate system, such that x comma y is in the relation f. So remember, this is a relation is a subset of this set. So we have to make sure that the coordinate x comma y also belongs to the relation. Okay? If a relation is defined by an equation, okay, in x and y, the graph of the relation is the set of all xy in the xy plane that satisfy the equation. So if we have an equation for the relation, all we need to do is to check the equation. We check all ordered pairs satisfying the equation. Okay? Now, we recall alternative definition for the function. Of course, if you have a function f from x to y, it is also a subset of x cross y such that for every x inside x, there is a unique y in y such that x comma y is in the function. So this is just a recall. Okay? With this definition, we have the following remark. The set xy, where x is in capital X and y is in capital Y, defines a function if no two ordered pairs have the same x coordinates. Okay? This means using the graph of this function, okay, or of the relation, we can determine whether that relation is a function or not using this theorem called vertical line test. The set of points in the xy plane is the graph of a function. Okay, so the set of points in the xy plane is the graph of a function if and only if every vertical line intersects the graph in at most one point. So every vertical line intersects the graph in at most one point. So this time, aside from observing the this set, okay, this set, we can just try to observe the graph in order to determine whether the set is a function or not, or the equation is a function or not. For example, you have your y equals x squared. The graph of this is this guy here. It's a parabola. And we will talk more about this later in our course. But this is the graph of that y equals x squared. The vertical line test tells us that if we get a vertical line in anywhere here, the vertical line will only intersect the graph once. So for example, for this vertical line here, this is the only intersection. For this vertical line here, this is the only intersection. For this vertical line here, this is the only intersection. If we get other vertical lines, say this vertical line here, it will only intersect once here. If you get other vertical lines, okay, say this vertical line here, you will only have that intersection. So at most 1 point. So this equation here, y equals x squared, it defines a function. Y equals x cubed. So this equation here, the graph is this guy here. And this is also a function. Meaning, if you get any vertical line, it will intersect the graph just once. Okay? Or at most once. Okay? So you get this vertical line here. You'll just get that intersection here. If you get vertical line here, you'll just get this intersection. If you get some vertical line here, the intersection will be somewhere above here. Okay? If you extend here, if you extend the graph. So just 1 point, or at most 1 point. Here, x equals negative y squared. So x equals negative y squared. The graph is this guy. Okay, the graph is this guy. But notice, if I get this vertical line here, okay, there are two intersections. This guy here and this guy here. And because of that, this equation does not define a function. Because there are two intersections already for this vertical line. If you get this vertical line, the y-axis, it will intersect once, which is fine, but it does not prove anything. If you get the vertical line somewhere here, this vertical line does not intersect the graph. It is fine, again, but it does not prove anything. This vertical line, however, or maybe this vertical line, or this vertical line. So for this vertical line, you have two intersections also. For this vertical line, you have two intersections also. So any of these vertical lines here, maybe vertical line, another vertical line here, any of those will prove that this equation is not or does not define a function because of the existence of two intersections. Okay. This equation, x squared plus y squared equals 1. So you have the circle here. So this is an equation of the circle. You have a circle here. You get the vertical line maybe here. Maybe somewhere here. This vertical line does not intersect the circle, but it does not prove anything. If you get the vertical line, x equals negative 1, it will intersect the circle at this point only. But it's not enough to prove that this is a function because you need to consider all vertical lines. But because of this vertical line here, you got two intersections, or maybe your y-axis, it's a vertical line. You got two intersections here. or maybe you put some vertical line here, you will also get two intersections. Because of those vertical lines, they prove that x squared plus y squared equals 1 does not define a function. Okay? So, any question with the use of vertical line test? Take note, the vertical line test tells us that you need to use every vertical line. And there are infinitely many of them. Okay? This vertical line test, it's a good way, it's a good test to prove that a certain equation or a certain relation is not a function. It's hard to use, this guy here, it's hard to use if you want to prove that the certain relation is a function, because you need to consider all the vertical lines. Okay? So in here, you need to consider all vertical lines, and that's infinitely many of them. Similarly for this, you need to consider all vertical lines, and there's infinitely many of them. On the other hand, for this, you just need one example of a vertical line. You just need this vertical line. You got two intersections. That's it. It's not a function. You just need this vertical line. You got two intersections. That's it. It's not a function. Okay? Question?
So we have just two function. That's it, yeah.
Yeah, at least in this example. Yes.
Mm-hmm. Do we'll have in Saturday some Zoom class or not?
Saturday? No.
Nothing. Yeah. If we have question about this, if we do.
Oh, during my office hours on Sunday.
Oh, Sunday. Okay.
Yeah, during my
What?
office hours.
How we need to enter or just
We use
same?
the same link. Yes.
Okay. Thank you. That's it.
You're welcome. Other questions? Now look at this. Given the graph of a function, we can identify and give information about the function. Okay? So note that if x comma y is on the graph of f, this means y equals f of x. So the y here equals f of x. For example, suppose we have this graph here. Okay? And this point, you see, negative 3, comma, negative 1. Here you have negative 3. Why is this negative 3? Sorry, this should be negative 2, comma, negative 2. Okay? This guy here should be negative 2, comma, negative 2. And then this guy here, of course, this is the origin. And this guy here, it's your 1, comma, negative, your 1, comma, 1. Okay? So let's see. So again, please take note of this. This should be negative 2, comma, negative 2. But anyway, here we see f of negative 3. So f of negative 3, it's equal to the y coordinate, which is negative 1. Okay? So I will have to do this every time. You have here negative 2, comma, negative 2. And then here, f of negative 2 equals negative 2. Okay? So this guy here, it's negative 2, comma, negative 2. So f of negative 2, because your x here, it's negative 2. You evaluate that negative 2 in f, you still get negative 2 because of this. Okay? Here you have f of positive 1, it's equal to 1. It's coming from this. So again, let me replace this negative 2 comma negative 2. But anyway, you have your 1 comma 1. Therefore, f of 1 equals 1. Okay? So don't be confused. It's the same here, negative 2, but this guy here, it's your y coordinate. This guy here, it's your y coordinate. And it's consistent. This negative 1 here, it's the y coordinate here. Okay? F of 0 equals 0 because that's your origin. Okay? So f of 0 equals 0. So again, let me replace this with negative 2 comma negative 2. But yeah, f of 0 equals 0 because you're on the origin also. So again, the same, but this 0 here, it's the y coordinate of the origin. Next example, we have the function g, and this is the graph. So this is a function. Look at this. This point here, it's negative 4, comma, positive 1. And then you have your negative 2, comma, negative 2. That should be negative 2. That should be negative 2. And then here you have negative 1, comma 1. And then here you have your 0, comma 2. Okay? And then in here you have, if you look at this is 2, comma, negative 2. And then this guy here, it's your 4, comma 1. Okay? But anyway, g of negative 1 equals 1. So g of negative 1 equals 1. So this is your x-coordinate, that's your negative 1. So if you evaluate that g, you will get your y-coordinate, which is 1 here. So g of negative 1 equals 1. G of 0 equals 2. So you look at this point, your x-coordinate, it's 0, and your y-coordinate, it's 2. So g of 0 equals 2. And then there you have your g of negative 2 equals negative 2. So your x-coordinate, it's negative 2. The y-coordinate, it's negative 2. Okay? Now, let's talk about, let's have more from this graph. The domain of the function g, notice it's just from negative 4 to positive 4 because we don't see any graph before negative 4. We also don't see any graph after positive 4. So the domain, and you look at the graph, everything is taken into consideration between negative 4 and positive 4. You don't see any holes. Okay? You don't see any holes. Remember the hole? If there's a hole, it means it's not included. So you don't see any hole. So the domain will be from negative 4 to positive 4. Okay? And then we also get the range. The range are the y values. But notice, the y values. The lowest value for y, it's negative 2 here. The highest value for y, it's positive 2. And all the y's, since you don't see any hole here, okay? You don't see any hole, okay? All y's between negative 2 and positive 2 inclusive are in the range of G. You don't see any graph below negative 2 or above positive 2. So this is the only range of our function g. Okay? Question? Okay, so that's it from me for today. So I want you to work on as many problems as you can on pages 90 to 94 of the 016 module. Okay? And yeah, uh, thank you for staying. If you have more questions, feel free to ask them now. Okay?